Good morning. This is a meter rule. It's used for measuring things and also drawing straight lines. And straight lines are very important today because that's what we'll be looking at in this episode of physics, CSEC physics that is, with me, Marvin Lee. Today we look at straight line motion with the help of our friend, the meter rule. Let's go. Straight line motion is motion along a straight line. It's one path. It's basically like moving from this end of the ruler to this end of the ruler. You're traveling along this ruler on a straight line and you're not traveling on any other path. So that's it. Only motion along a straight line. No other paths allowed, no other paths permitted. There are 5 terms that we have to define clearly. Speed, velocity, and of course, for those of you who might have done a bit of physics, you realize that speed and velocity are based on 2 different terms, distance and displacement. And then there's the king of them all, acceleration. So the 5 terms we have to define are distance, displacement, speed, velocity, and finally, acceleration. Let's begin. Now, putting down my trusty friend, if we are to travel from A to B along our blue line, we are going to need to take some measurements in order to analyze how motion occurs from A to B. The first 2 terms are distance and displacement. Now, distance is a scalar. It's simply how far you have traveled. That's all. It does not take direction into consideration. Displacement takes direction into consideration. Let me explain further. Suppose I travel from here to some random point on the line, let's say 10 meters away from A. The distance I have traveled is 10 meters. However, I could also travel 10 meters from B. It's just a distance. Displacement will clearly state whether I have traveled 10 meters leaving A or 10 meters leaving B. Displacement is distance in a specific or specified direction. That's displacement. Now, in simple terms, distance is just how far you traveled. Displacement is how far you traveled in a particular direction. So, since we're on a straight line, the 2 can be the same in terms of magnitude or quantity. You can have 10 meters of distance and 10 meters of displacement. But the difference is displacement is going to tell you in which direction you travel. So displacement again can be from A or from B or to A or to B. Now, distance and displacement, they're interchangeable only because their magnitude, the number that they represent, can be the same. That's it. Nothing else. Okay? Remember that. Having defined distance and displacement, we now move on to speed and velocity. Speed is the rate of change of distance. In other words, simply put, is just how much distance you've covered in what period of time. That's it. How much distance divided by how long it took to cover that distance. Velocity is the rate of change of displacement. And it's similar to speed in that it is how much displacement covered in how much time. The difference is basically just like distance and displacement, it's direction. Speed, again, does not take direction into consideration because speed is based on distance. Velocity takes distance into consideration because velocity is based on displacement. And just to recap, I know I said it before, distance is simply how far you've traveled. Displacement is how far you've traveled in a given or specific direction. So these 2 will be the same numerically. They can have the same value along a straight line, but speed won't take direction into consideration. Velocity will take direction into consideration. So 4 terms defined. Distance, how far you've traveled. Displacement, how far you've traveled in a given direction. Speed, your change in distance divided by how long that change took to occur. Velocity, your change in displacement divided by how long that change took to occur. Now we have one more term to define, and that term is acceleration. So this is our little friend. Do you need to move, Alex? Okay, good. Glad you didn't need to move, but you could edit that out too. Acceleration. Now, acceleration is very important because acceleration is the change in velocity over the time taken for that change to occur, and acceleration has a formula. It has a formula. Acceleration is equal to v minus u over t. V is your final velocity. U is your initial. And t, big guess, is the time taken for this change to occur. So this is your change in velocity. This is the time taken for that change to occur. And this is your acceleration. So, simply put, if you're moving faster now than you were 1 second ago, you have accelerated. If you're moving slower now than you were moving 1 second ago, you did accelerate as well. But the tricky thing about that is there's another word for it. We don't call it acceleration all the time. We will look at that other word a bit later. For the keen among you, you might have noticed that I did not mention units. I know I did not. Distance and displacement are measured in the same units, meters. Speed and velocity are measured in the same units, meters per second. M/s or ms to the minus 1. And acceleration is meters per second squared. Okay? Please don't say ms minus 2. It's not ms minus 2. It's meters per second squared. ms to the minus 2. ms to the minus 2, okay? Just remember that. Small details. Now, having done this, we have to move on to graphs. And this can be very, very tricky. The syllabus requires us to look at two graphs. We have to look at the displacement time, and then we have to look at the velocity time graphs. Now, we are not going to be plotting these graphs, so please don't feel you have to break out graph paper and rulers just yet. You just need a pencil and the ability to draw a line that's close to straight. Once you could do that, you'll be fine. On to graphs we go. Welcome back. Now, as you can clearly see, I have recruited the help of Mr. Stick. Mr. Stick is here to teach us how to plot, or in this case, sketch distance time graph. Now, let me explain the difference between a plot and a sketch. A plot is where you actually get a scale and you get distances and you use graph paper. A sketch is where you roughly use points to indicate just the general shape of the graph. And that's all we're doing here. We are sketching, not plotting. Now, in very brief terms, sketches don't have to be precise or accurate. They just have to be general. The other thing I have to point out is that this is a displacement time graph. Displacement time. Displacement, the first quantity goes on the y-axis, and time, second quantity goes on the x-axis. Now, I have my two axes roughly sketched. If you notice, my lines aren't perfectly straight. They never are, but I'm just pointing that out. Displacement is measured in meters and time is measured in seconds. So, let us begin by looking at Mr. Stick. Mr. Stick is going to run a 100-meter race. So this is the starting point because this is marked as 0, and forgive me for forgetting the unit, 0 meters. So I have the 30-meter mark indicated on my racetrack. So Mr. Stick starts at 0 meters. Now, 0 along this axis, the y-axis, essentially is the x-axis, okay? So he starts from here and he gets to 30 meters. Let's give him a time of, well, Usain ran it in what, 9:58? Mr. Stick ain't that fast. Let's give Mr. Stick 4 seconds. 4 seconds. I know that's pretty slow, I think. Anyways, so this is our first point. Mr. Stick runs his very best and he gets to this point. Now, Mr. Stick gets to this point and a cramp gets Mr. Stick. So Mr. Stick pulls up immediately. He stops running. If Mr. Stick stops running, just doesn't even walk or move at the 30-meter mark, his displacement will not change. Now I'm using the term displacement and I didn't explain this, but you should know that if he's starting at 0 and running to 100, his displacement is measured from here. You don't move the start line in a 100-meter race, you don't move it. It stays stationary and you move. So if Mr. Stick stays still and he doesn't go forward, his displacement remains constant. Now our boy has a bad cramp and Mr. Stick stays. At 30 meters, this line should be broken, forgive me for that. I'll make it broken now. Ta-da, broken line, good. He stays here for, let's say, another 10 seconds. So from here, he stays at this distance for 10 seconds. So 4 plus 10 gives you 14. Finally, Mr. Stick continues on and his displacement, again measured from the start line, increases until Mr. Stick reaches the end of the race. I've run out of space. And he reaches the end of this race in, let's say, another 8 seconds. So 8 seconds from here would be a whole 22 seconds. And this is the race. This is how his motion will be plotted on a displacement time graph. He starts here. His displacement goes up to 30. He catches a cramp. He doesn't move for 10 seconds. And then he runs the rest of his race very bravely, getting to, this is the 100-meter mark in 22 seconds. So you notice that we have 3 different portions of motion. And usually when an object moves, you don't have just one straight line. You can, but it's not as common as you think. I mean, when you're, for example, in a car, you don't just leave your house, drive at one speed, never stop, and get to where you're going. You don't do that unless you're going to the corner, probably. But there are different portions, and each portion means something. Here we have displacement increasing with an increase in time. How do I know displacement increases? Because it moved from 0 to 30. How do I know time increased? Because it moves from 0 to 30. Now you might be thinking, why are there 2 zeros? Why are there 2 zeros there? This is the origin. And the origin means displacement and time are both 0. So it's 0 for displacement and 0 for time at the origin. So with an increase in time, there is an increase in displacement. For this portion, however, with an increase in time, there is no change in displacement. It means he stays at 1 point. And then, in the next 8 seconds, Mr. Stick's displacement increases because he reaches the end of the race. And again, he moves from 0 meters to 100 meters. And he took a grand total of 22 seconds to finish a race that one very tall Jamaican finished in an astounding 9.58. Now, you might be thinking, so who is this? Just a little trick question. If displacement is measured from this point, increasing in that direction, would Mr. Stick have displacement, or could he have displacement in this direction? The answer is yes, he can. Why? If his displacement increases, and we call it positive over here, if he walks in the opposite direction, let's suppose Mr. Stick got into the starting blocks and realized, you know what, this is not going to be my day, and he just turned around. His displacement would not be positive, it would be negative, because he's moving in this direction and not that direction. So displacement can be negative, because if it's measured from this point, the start line, going in that direction can be positive, and going in this direction can be negative because he's not moving in the positive direction. So displacement can be either positive or negative. And the reason for these signs is that it allows us to differentiate direction. He's running to the finish line and he's not running to the finish line. Displacement time graphs. Tricky, yes, but still easy to understand. Let me go it over one more time, just in case. He starts here. When he starts here, with increased time, we have increased displacement. And this portion here, this piece, indicates that there is no increase in displacement while there is an increase in time, implying that here, Mr. Stick does not move. He stays right where he is. So, displacement time graphs, your friend. And remember, since these are sketches, not plots, my distances don't have to be realistic. This could have been, I could have said that this here is 40 seconds. There would be nothing wrong with that. And I could have said that this is just 4 seconds. Because of the fact that this is a sketch and not a plot, there is no scale applied to the axes. So please, on a sketch, don't take distance to actually mean anything. All right? It's just done to give you a general idea of what the shape of the graph should be like. And this is the shape of our graph. Anyways, with that completed, we now have to move on to velocity time graphs. And these promise to be fun. Having looked at the displacement time graph, we have to look at this one now. Now, the velocity time graph is more useful than the displacement time graph. Let's just start there and you shall see why. So, velocity, time, velocity on the y, time on the x. I have my axes sketched and I have my units and I have a graph with some dots. Now, for both displacement time and velocity time graphs, every straight line is a section or a portion of the journey or motion. Now, since we are looking at not just straight line motion, but uniform motion on a straight line, our graphs are going to be straight lines. All right, just accept that as fact for the moment. Now, we have phase 1, phase 2, phase 3. And I put the 4 blue dots to indicate something. Phase 1 starts here and ends here. Phase 2 starts where phase 1 ends and ends here. Phase 3 starts where phase 2 ends and ends here. So these points are both the end of one phase and the beginning of another. So phase 1 ends here. Again, I'm repeating myself. Phase 2 begins here. Phase 2 ends here, phase 3 begins here, and phase 3 ends there. So let's use our big brains and figure out what happens here. Now, remember this little formula? Acceleration is change in velocity over time. So this is where we start, this is where we end. V is where we end, and U is where we begin. So if you notice, V is much higher than U. And this here, this is our time. We have a change in velocity over time taken. Please note that between V and U, velocity increases because U is way down here and V is way up there. You know, increase. Yes, it moved from 0 to a higher value. So this here is acceleration, okay? Acceleration. So phase 1 is acceleration. Meaning whatever was moving, human, car, fly, bus, whatever it was, it sped up, it got faster. Now let's look at 2. 2 is a horizontal line. This is where 2 starts. This is where 2 ends. There is no change in velocity between the beginning and the end of the second phase. In other words, phase 2 is no acceleration. That should be an L. Or it's called constant velocity. Why? There's no change in velocity, so velocity is constant. And there's no change in velocity, so there is no acceleration. Okay? And then 3. Now I had mentioned earlier that that if an object slows down, we have to be careful what we call it. So let's look at 3. My chalk just fell out of my hand. Apologies for that. This is where 3 starts. This is where 3 ends. Final velocity, initial velocity. There is a decrease in velocity because u is way higher than v. Where we started is far higher than where we ended. So there is a decrease in velocity. If we did the math, let's just use some random numbers. Let us say that this is 10 and that is 0. 10 and 0. If you just do the math for a second, the formula says it's final, which would be 0, minus initial, which would be 10. 0 minus 10 is minus 10. That means the numerator would be negative. It means that we would have a negative value for acceleration, okay? Because you ended up with far less than you started with. So there's a negative value attached to that. Now, the term for a negative value of acceleration is actually deceleration, okay? Now, if you're asked in a question to find acceleration and it's negative, you can call it deceleration. And you can also leave that negative value in to indicate that you are slowing down. That's what negative acceleration simply means. You're moving slower now than you were previously. So, for this velocity time graph, the first and most important thing is that the gradient or slope of each portion gives you acceleration. Gradient or slope gives you acceleration. So an upward slope means you're moving faster. No slope or horizontal line means you're moving at the same velocity, and a downward slope means that you're moving slower. Faster, same thing, and slower. Faster, same velocity, slower. That's it. Now, not only does this graph give you acceleration, and not only can it tell you velocity, it can give you one more important thing, and that is the area under the graph gives you your displacement. Okay, area under the graph. Now, since you're on a straight line, the displacement is actually the distance you have traveled. Okay, so area under the graph. Now, I like breaking my graph up into these 3 portions for this reason. You can find the area under the graph by finding the area of this triangle, this rectangle, and this triangle, and you can add them up, or you can simply find the area of a trapezium. Okay, now the formula might appear difficult, but it's not. So I can go it over again. Area under graph, which could be the sum of this shape and this shape and this shape, or you can simply find the area of the total shape or the whole shape, is displacement. Okay, now we have to work 2 problems, just two. The reason we have to work 2 problems is that this topic requires a ton of practice, and I hope I can show you how to navigate the little intricacies that might pop up or might challenge you when it comes to working these questions. So let me go over again before we go to our first problem. Gradient is acceleration. Area on the graph is how far you've traveled. And this is why a velocity time graph is the most useful graph when it comes to analyzing straight line motion. On to our questions. Welcome back. This is our problem, and let us go through it slowly. Now, before I forget again, one of the things that has to happen is whenever you're given a problem, you always need to figure out what information you have been given before you move forward. You can't just decide you're going to work without knowing what you have. So my tip is just underline everything. A man walks 10 meters from his gate in 6 seconds. He stops to check his pockets for 10 seconds before returning to his gate. And forgive me, I should have put in 8 seconds. Here, display this data on a displacement time graph. Now, 10 meters, 6 seconds, 10 seconds, his gate in 8 seconds, and displacement time graph. So, it means that we should have a graph that has time here and displacement here. So he walks 10 meters from his gate. We're measuring displacement from his gate, so 10 meters, first mark. That being said, the time taken is a whole 6 seconds. So this is the first portion of motion. Okay, first part of everything. First portion of motion is what I just said. It should be portion, forgive me. Now, the second thing is that he stops. He stops to check his pockets, meaning he is not moving from his gate or back to his gate. He just stays. For how long? 10 seconds. So it's not 10 seconds from the start. It's 10 seconds from when he stopped. So we stop at 6 and 10, if my math be correct, be 16 seconds. And then he returns to his gate. What does that mean? Now, returning to his gate means he's not moving away from his gate. He's moving back to his gate. Okay, he's going back to his gate. So how do we show going back in, or on rather, a displacement time graph? Well, it's really simple. If going away from your gate means the displacement is increasing, going back to the gate should mean your displacement is decreasing. And it decreases in 8 seconds. 8 seconds from where? Not 8 seconds from the beginning, not 8 seconds from here, but 8 seconds from the end of the portion of not moving, which is here. And 16 and 8, last I checked, was 24. I don't know if it has changed in 2020, but this is our displacement time graph. He starts at his gate, he moves 10 meters from it in 6 seconds. Then for another 10 seconds, he stays at 10 meters. So from here to here, there should be no increase or decrease in the value of displacement. And then in the next 8 seconds, he goes back to where he started, which is his gate. And if displacement is measured from his gate, it means that he should have 0 displacement at the end of that 8-second period. So away from gate, stopping to check pockets, back to gate. Total of 10 meters in, not 10 meters, 10 meters from his gate, 10 meters back to his gate in 24 seconds. This is a sketch of a displacement time graph showing how far he traveled. Now, I did not explain this in the first example or in explaining displacement time graphs. So there is a gradient attached to this graph as well. The gradient of a displacement time graph gives you velocity. Okay, the gradient gives you velocity because you have a displacement, change in y, divided by time, change in x. Gradient of a graph is always and forever will be the change in your y value divided by the change in your x value. Displacement divided by time, y divided by x. So the gradient of this graph will give his velocity, which brings me to another point. Just because you start at the origin does not necessarily mean you are starting from rest. I know we tend to think of it that way, but on a displacement time graph, that assumption cannot be made. All right, let me explain briefly why. Now, assume that someone is, you're looking out the window and someone is running down your street. You're only going to see them for that moment they're in your view, like they're in your window, or you could see them through the window. So when you start to see them, if you measure displacement from the moment you see them, that does not necessarily mean they weren't moving before you saw them. Or it's like when you see a car fly past. The car is moving way before you saw it. It does not mean that the instant you see it, it starts moving. It was moving before. So on a displacement time graph, we cannot assume just because an object starts at the origin, its velocity is 0. It can be moving, but you measure displacement from a certain point. Movement before is not determined by this. That is why a velocity time graph is more useful, because it can tell you that an object definitely and definitively starts from rest. So, man walking, man turning back, displacement time graph. On to our velocity time graph. I hope I can make that one interesting. Having looked at the displacement time graph we have to look at this. A car starts from rest and reaches a velocity of 12 meters per second in 4 seconds. It then maintains this velocity for 2 seconds before coming to rest in another, my English teacher would kill me, another 10 seconds. Display on a VT graph. So, VT, velocity time, velocity time. Now, when it comes to motion, we can describe the motion of an object in a few ways. I will come to that shortly. So first thing is that it reaches a velocity of 12 meters per second. 12 in 4 seconds. So again, people, this is a sketch. It does not have to be perfect. It then maintains this for 2 seconds. 2 seconds from where? Not from the start, but from 4 seconds. So 2 and 4 gives us a grand total of 6 seconds. Before coming to rest in another 10. Now, coming to rest simply means that its velocity becomes 0. And its velocity is 0 anywhere along the x-axis. Okay, so basically this line goes back to the x-axis, and the time taken to come to rest is measured from 6 seconds, not from the start, not from 4, from 6 seconds, and it's another 10. So 6 and 10, 16 seconds. And this is our velocity time graph. Fairly straightforward. Let me ask a few questions. Now, first off, actually, yes, I'll ask them. There's an acceleration for the first part. There's a deceleration for the last part. This is your initial velocity u. This is your final velocity v. Acceleration for the first part is v minus u upon t. Velocity at the end is 12 meters per second. At the beginning, it is 0. And the time taken is 4. Simple maths. Answer is 3 meters per second squared. This is how it is written, okay? Now, this is important because instead of saying it reaches a velocity of 12 meters per second in 4 seconds, I could have said it accelerates at this rate for that time. At 3 meters per second squared for 4 seconds would still give you this shape. So there are different ways of describing motion when it comes to velocity time graphs. I could say acceleration and time, or I could say the velocity it reaches in a particular time as well. Do make note. Now, for the final part of the graph, the very final part, this is where it starts and this is where it ends. The deceleration is change in velocity over time taken. And again, with a bit of, you could always pause this and grab a pencil. I will attempt to use my brain. It's 12 divided by 10. And the answer should be minus 1.2 seconds. Meters per second squared. Oh, Father, forgive me. My physics teacher would kill me. The change in velocity is 12 meters per second. The time taken for this change is 10 seconds. Now, I said 12 meters per second, but if we're actually correct, if we were to use the correct terminology, it should be minus 12. Why? Again, because it's 0, where we end up, minus 12, where we started, upon 10. And this is minus 12 over 10, and the answer is negative 1.2 meters per second squared. Now, this is my acceleration. If I said deceleration, I would take this off. I wouldn't need to put the negative sign because deceleration already implies I am slowing down. Okay, so acceleration, deceleration, shape of graph. One more thing. Area under graph. Now, you have your two ways, and I'm going to leave the longer way to you. You have pencil, paper, and the pause button, your friends. One shape, two shapes, three shapes. We can find individual areas, which is not wrong, or you can find the area of the total object. Now, the area of this shape, and just to be clear, this is our shape. Yes, I know I'm shading it like I'm in primary school, but this is our shape here. Okay? When we say area under the graph, we actually mean area bounded by the graph and the x-axis. That's what we mean, okay? So, I hope our teacher sees my coloring skills and can give me a good grade. Area under graph means the area bounded by this shape and the x-axis. It's a trapezium, and the formula for the area of a trapezium is half the sum of parallel sides by height. You might be thinking, parallel sides, what is this man talking about? Now, this side is parallel to this side. I know it doesn't look parallel on my diagram, don't laugh at me, but they're parallel. And this is the height here. So, this here is 2. The straight portion, the horizontal portion, I said straight, Father forgive me, the horizontal portion is 2. This is 16. This is 12. So let's do some maths. Mental. Now, I believe in mental because I'm a dinosaur and we used to get licks in primary school for not being able to do mental. I know y'all don't have those struggles. You never did. Kudos. But if I can add correctly, 16 and 2 are 18. 18 divided by 2 be 9. 9 by 12, 108. The displacement is 108 meters. Go it over again. Parallel side 1, parallel side 2. 16 and 2 make 18. 18 divided by 9, sorry, by 2 is 9. And 9 by 12 is 108. Reason being, the formula is, you could write this down, half the sum of parallel side and parallel side multiplied by height. 16 and 2, 18 divided by 2, 9, 9 by 12, 108. And that's it. Now, big disclaimer. All graphs don't have to look like this. All graphs don't look like this. All right? Please don't think that this is the only shape that can come. No, it's not. All right? Each situation has to be taken and interpreted correctly. All right? I can have a case where the car starts here, or you start to observe the car when it's at 12, the graph could go down, could come up, it can look all kinds of crazy. All right? The situation and the motion has to be analyzed, all right, correctly. So please, I'm begging you, don't say Sir Lee said that is the only thing it could look like. I do not say that, all right? So, gradient is acceleration and area is distance traveled. Please remember this. Now, just to wrap up, we looked at 5 terms and 2 graphs today. Forgive my very chalky hands. Part of being a teacher. The 5 terms we looked at were distance, which is essentially just how far you move along a straight line. Displacement is distance along a straight line, but in a given or particular or specific direction. There is speed, which is change in distance over the time that change took. There is velocity, which is change in displacement over the time that change took. And then there's acceleration, which is change in velocity over time that change took. And then there are 2 graphs. Our displacement time graph, where displacement is on the y and time is on the x. And for that graph, our gradient is our velocity, and that's all we can say from that graph. And then there's our velocity time graph, which is way more useful. It can tell us if an object starts from rest, it can tell us how fast the object goes, and it could tell us also how far the object traveled. So, please remember these 5 terms, these 2 graphs. Stay safe, and I will see you in the next episode of CSEC Physics, with me, Marvin Lee. Take care.